Good morning, welcome. I'm not sure why you came, so I'll try. Who came for type safe? Okay, who came for efficient? And who came for low level? Okay, let's see. Motivation. What does this mean? Yes, some of you programmed in, I don't know if it's Pascal or whatever language, so it could mean not equal or equal or whatever. So most of the time we deal with programming languages which are non-intuitive. So we don't know what the things mean. Another thing is the font. Who uses still fixed width font in his editor, like Courrier or something? Who uses, how you say, proportional font, like Times? Okay, this is, if you still use a fixed width font, it's like using a punch card, because this is a thing we did 50, 60 years ago. Now we have different devices, and we can change things, and we should use them. So this is another example now in a proper font. What does this mean? As a Java programmer, you will say this is an assignment. If you ask somebody coming from school, he doesn't know that this is an assignment. So again, things are non-intuitive. What I wanted to do almost 20 years ago is to have a new programming language which supports what I know from school, which is mostly mathematics. So this means x is equal to 2, and not 2 will be assigned to x or whatever. And we now have Unicode, which means that we can use other tools or characters which are more precise. In this case, it simply says x is not equal to 2. So this is what I wanted to do. Now, 20 years later, I'm allowed to do it. I'm allowed to write a programming language because I can. There are several other people who have done it, and I don't know if it's good for anything, but I can do it, and so I'll try. In 1992, I read an article from a guy who said that a programming language is independent of several things, and the things are the machine, the problem, the humans, and the time. So what I wanted to create is a language which will be independent of the machine, independent of the problem, independent of the humans who will program with it, and independent of time. This is, of course, not possible, but I try my best. And he defines what independence means, and one thing might be interesting. He, for example, said, run any program written for one architecture on any other architecture. So this was 1992, and you remember in 1995 we had Java, and Java had the promise, write once, run anywhere. So it seems that some of these goals are possible, and so I'm still optimistic to achieve my goal. That you know why I created the language is it's a whole family, and the idea between of this family is that you can address several problems. And I want to use only 3 different syntax elements. The first element is a keyword followed by a token list. I don't know what the tokens mean. The compiler extender has to define what this means. For example, you know the import statement, so it's followed by a package name, and the package will be imported. Another thing is a block statement. It starts with a keyword, it will be followed by several tokens, then there will be a begin keyword, and everything will end by an end. So you as a Java programmer will say, where are the curly braces? I don't have curly braces for this purpose, because I wanted the things to be similar in every level. And then, of course, I have expressions which are function calls or something else. So let's take a look at an example. You have a namespace, and you see the tokens are like a URI. So it's a little bit different than in Java. But then you have a function. The function gets integer values and returns an integer value. You see there's an assignment. The assignment with a colon means that it's also a definition with type inference, so we know that z will be probably an int. Then you see a block. By the way, the function, of course, is also a block. You see it starts with a function. The begin keyword is. Within the is and the end is the block, whatever the block does. So for a function, we know there are instructions, commands, and you see the if, so it's again a keyword, and if a keyword is allowed, is defined by the block. So it's fairly simple and extensible. And for example, if you want to add a try and catch, it's very simple. You define a new syntax element, which starts with a try, and then you define the rest in a special manner. The funny thing is that syntax elements can be imported, which will avoid the problems Java has if they introduce new elements. You remember the enum thing, and you simply can say import enum, and then the enums are only available where you have imported them. So that's the plan. I have several levels, and the one level we are interested in is the level 1. This is because we only do things which can be managed by a virtual machine. For example, the Java virtual machine. On a lower level, we have things like give a pointer a specific address. For example, you have a device and you assign the address of the device to the pointer. This is not possible with Java, so we have to omit this. And on a higher level, we have things like control structures, like if and so on, because the level we are talking about is strictly based on the virtual machine. But we will see that. So what we can do in the several levels is, especially in level 1, we have managed memory, and in level 2 we will have control structures, records, and so on, and in level 3 we will have object orientation, and so on. We have, of course, object orientation also in the level 1, but in a low-level manner. Okay, so it might look like this. We have the JVM at the bottom, and above that we write our code. If necessary, we can also use the lower level, and what I plan for the future is, what Java also tries to do, is that you can use the CPU without using the JVM and without explicitly using the Java native interface. So if you need any special things from the CPU, you can use them by using the level 0, and you don't need the JVM for that, and you don't need to care about the binding via JNI. Another thing which I think is very useful is that you can have some sort of protections. So if you don't want your developers to work with the level 0, you can simply say you're not allowed to do that. I think this is very important, because if you have pointers, the people will use the pointers even if you don't want it. So you can simply say this is privileged, and you can only use it if you have the proper privilege. And you see that an application can base on the several levels. So you have higher level things, lower level things, whatever is needed for your application. Okay, now let's go started. Last thing. The file format is a binary format. If you only use the text, you can still use it with a normal text editor, but usually you will embed pictures and so on for the documentation. And so there's an internal file system, and the internal file system allows to store those binary data. What I think is very useful is that there's a supported version, and the compiler options are embedded in the file. So this is very useful if you have a special algorithm which requires special options. Then you can put the options where you need them, and not yeah, if you don't know that you have to translate it with a special option, then the information might get lost. So you put everything in the file, even if you like to, the version history, change log, or whatever you like to do. Okay. Who deals with bytecode? Okay, for everyone else, I have a short introduction how the JVM works and why I've built this level 1. And yeah, the JVM is a stack-based machine. This is very useful because if you read the bytecode, you can do it very quickly, and you can build a syntax tree very quickly. So the bytecode is a very good idea. Let's look at an example. We have a small class here, simple, and the simple class has two things. One method f, which simply does something, and one method half, which divides the given parameter by 2. So fine. Then we have a main, and the main creates a new simple, then calls the f method with 37 and 44. If we translate this, we will see that the main things stay the same. So we have the signature above, it's the same. And it will be encoded in some manner, which is not very interesting, but necessary if you have to deal with bytecode. And you see here the bytecodes. So it says iLoad, which means that the int will be loaded from the position 1. I will show you in detail in a short moment. And you can see if you have little instructions on the left side, you have little instructions on the right side. Let's take a look at the other thing. You see now it's becoming more complicated because we have local variables, we call a method, and you find this all here in this bytecode. Just to show you how this works, the main method is more complicated, looks more complicated because long things are standing here. This is because if we use a static variable, then we need to define which field is used. So for example, if you look at the instruction 8, get static, number 28, and the number 28 refers to the constant pool in the bytecode. The constant pool contains all the strings and all the information, meta information needed to run a program. And you see that the position 28 marks a field, the field Java lang system out, and this is of type Java IO print stream. Whenever you deal with a object, then it's surrounded by an uppercase L and a semicolon. So we know what this means. Above, we, for example, see the init method. The init method has a special name surrounded by those angle brackets. And you see it has no parameters because the parentheses are empty, and it returns nothing. So it's void. So this is the encoding, and it's quite interesting. Below there you see the method f is a method which takes two integers and returns an integer. We are only interested in this part. We will take a look what happens if we run our code from instruction 11. So first we load from somewhere an address, and we put the address on the stack. Then we push the value 37 onto the stack, then the value 44, and then we call the method f. The method f is from the class simple, and because we are in the class simple, the main routine is in the class simple, we don't need to say where to find it, because the bytecode, the class says use this method. Okay, now something happens, and I don't know if the values will be copied or whatever, but for the called function, it looks like this. We have the address, and it has the name this in our Java program, and it stands at the position 0. Then we have the 37. This is in our program X, and it's at the position 1, whatever that means. So our stack is now accessible, and we can explicitly access the values 0, 1, 2, and 3. The 3 we know because we had one local variable r, and this local variable now is on top of the stack, and we can access it with the number 3. We can't do anything else. Everything else is just stacked. And we know that because every method has to give the information about how large the stack will be and how many local parameters I use. And the parameters from the function are treated as local parameters. Okay, so let's start. First we load the value at position 1. So the 37 is on top of the stack. Then we load the second element, which is the 44. Then we add both, and you see both elements has been removed, and the result from the add function is on top of the stack. Then we store this element at position 3, so we can read it later. Then we push the address on the stack, then we load our stored 81, and now we call the function half. We don't know what the function half does. It works the same way, and the result will be pushed on top of the stack. So you see the address and the parameter have been removed, and now the result is on top of the stack. And now we store this element in our local variable. Then we load it again, and you see, if you take a look at Java bytecode, you see a lot of things you might think are not necessary. For example, we made a store and then a load. So we could have omitted this. But the Java compiler is, let's say, not very bright. So he says, let's do the thing in a very simple way. But the just-in-time compiler is very clever. And he needs simple things to make more optimizations. This is a problem we have. If you try to write code in the assembly language, then you have to be very careful what you do. If you are too clever, then the just-in-time compiler cannot cope with whatever you have done and cannot optimize it as good as it could have been if it had been a little easier. Okay, then we push 50, then we compare both elements, and now we remove both elements and decide if the first element is greater or equal to the second. And if the element is greater or equal, then we jump to position 19. But because 40 is less than 50, we go to the next instruction. We push 50 again, and we return 50. So now the 50 is somewhere on the stack, but the stack frame is not needed anymore. And so we return where we came from, and we remove those elements and put the 50 on the stack. So that's how the Java virtual machine works. And the bytecode is pretty straightforward. It's very limited. We have several methods for several instructions for int, for long, for double, for float. If you have to cope with bytes, then you have to translate the byte to an int. You sign extend it, and then you work with an int, and then you have a method which allows you to shorten it back to a byte, and then you can store the byte wherever you need it to be. For example, in an array. Otherwise, you simply work with ints. This doesn't seem to be acceptable, especially if you want to do other things. For example, if you want to check if you have an overflow. This is very annoying if you have to do it in Java. Or you want to have unsigned arithmetic. So this is also impossible in Java. So I said I will build an assembler which allows me to do everything I need. And I will put it in the proper bytecodes. And I assume that those bytecodes I create are optimal. So you want to solve a problem by using unsigned values, you can do it, and I promise you I did my best that you don't waste any time doing this. Okay, let's take a look. We have data segments, and the data segments are like static variables in a class. The advantage is that you can put things in an arbitrary order. And if you take a look, you see that's a sequence of byte, and a sequence of byte means there is a sequence of 20 consecutive bytes lying there. However, I do this. It's not a pointer to an array or whatever. In our model, this really means we have 20 consecutive bytes. This might be useful for you if you need special initialized data. Then you can simply use it because you know the first 20 bytes are the greetings sequence. This example is not very useful because we have strings. We can use every Java function we like, and so we could do it in a better way. But let's simply assume we have a function print which, like in C, uses every character until we see a 0 byte. And then you use the target operator for the greeting, so they have the address, and then you give the address to the print, and the print will go through the byte sequence until it sees the 0. In most of the cases, you will use simply your Java stuff. So if you have, let's say, a real string, then it will be a reference to a string. So 4 bytes will be reserved for this string. Yes?
Why is the procedure ended by callable?
Yeah, because I changed it and I forgot to change it just before I started the presentation. In an earlier version, everything in this level was a callable. It seems to be very useful to know if a thing also on this level has a side effect or not. So everything is a callable, but a function is a special callable which has no side effects. A procedure is a special callable which has side effects, which the print does. Sorry. Here the same problem. Okay. If you deal with this low level, then you have new problems which you hadn't before. For example, if you read an int in Java, it is an int. If you have now access to the memory, the order of the memory is important. For example, if you say, I have a data segment with 4 consecutive bytes. The first byte has the value 1, the second byte has the value in x23, and so on. And now you access this as a tetra. Tetra means 4 byte. So if you load it and you start at address A0, then all these things will be interpreted in some specific way. And you don't know it if you don't know on which kind of machine you are. If you have a little endian machine, the value will be 6, 7, 5, 4, and so on. And if you're on a big endian machine, your value will be 1, 2, 3, and so on. So this is very important, and this might be a problem. So the language might be type safe, but you can do a lot of errors if you don't know what you're dealing with. So if you want to make sure that your program will only run on a machine where you have a big endian order, then you simply can make an assumption. So you say assume config byte order is big endian, and if you try your program on a machine which has not this byte order, it says sorry, this is wrong. It's the same if you want to run the AWT and you are on a machine where there's no screen, then it says to you, here's an AWT error because we are headless. Okay. Let's see how a program might work. I have a program which finds a 0 in a word, and we can do it byte-wise, but this is very slow. Especially on a 64-bit machine, it is more efficient to read the 64 bits and then try to figure out where the 0 is instead of going there byte by byte. Because if we do it byte-wise, then we have to check 8 times, and it doesn't seem to be a very good idea. So this is an example for an algorithm which marks specific bits. And we take a look at this. We have a mask, and this mask looks like this. So we have almost zeros, but in every byte, the most significant bit is 0. Then we add this mask to our original value, and you see that we will, we AND this mask. And so you see the most significant bit of each byte is still 0, and the rest is unchanged. Now we add the mask to it, and we will have an overflow. You see it here. We have an overflow whenever there is a set bit, because of our mask. With the addition, one bit will be propagated to this most significant place. Then we OR it. Then we OR it to have the first bit which we eliminated in the first instructions. Then we OR it. Then we OR it with the mask. And you see that we will have all ones if here's a set bit, and all zeros, and the most significant bit is 0 if there's no bit inside it. You see, this is a different kind of thinking, and if we invert this now, you see only one bit is set, and we don't need it an if to figure out the specific place. If you do this, this is a whole new world. We can do, of course, everything we did here we can do in Java, but Java doesn't seem to be the right tool for doing this. Yeah? If we go to a lower level, then we go to a lower level, which means we manipulate bits, we try to avoid comparisons because a branch is very expensive, a mispredicted branch is even more expensive, and so on. Okay. Now we have a problem. We have marked our bit, but we have to cope if we are in a big endian machine or a little endian machine, because this bit will be on a different place if we have another orientation. Because we have our bytes, we want to find the correct 0 byte, but if we load the bytes in words, tetras, octas, with 4 bytes or 8 bytes, then the order might be in the wrong place. So we have to cope with it, and my language offers a possibility which is a variant. It's like in C, if you have those if-defs, but you can only have correct code. The problem is with if is the if-def in C is that you can also put in things which are not valid for itself, valid C fragments, and so we have a possibility to define different algorithms which depend on specific preconditions. So we have two variants here. We have a big endian variant and a little endian variant. And if we take a look at it, we see if the config byte order is big endian, then we use number of leading 0 bits to find out which is the correct word, the correct offset in our byte stream. And if the byte order is little endian, then we use number of trailing 0 bits to find the correct offset. So for the proper, this is static, so for the proper machine, you have your assumption, and then it will be translated for this specific machine. This is not dynamic, so if you have your Java program and you run it on a wrong virtual machine, it won't work. Okay, types. These are the types I have. I could have given them proper names like machine word, like integer, like unsigned, and so on. You can still do it because these are only abbreviations. So we have machine words, and machine words are always p byte words, where p is a power of 2. So we have, for example, a byte, which is 1 byte. We have a byte, which is 2 bytes, 4 bytes, 8 bytes, 16 bytes. And this is unlimited, so if you need a word with 128 bytes, you can have it. And especially you can have an addition, a multiplication, division, and whatever function you need is available if you need 128 byte words. So it doesn't seem to be very useful because it's not very efficient. 128 bytes are very hard to load, but it's possible. You don't need to care about it. So if you need 128 bits, it's a lot easier. Then you have 16 bits of, let's say, 32 byte words. This is something you might need, and so you don't need to care about them. We have, of course, machine words are bit patterns. We don't know what they are. They have no meaning. They simply have bits. The integer, then the bits will be interpreted in a proper manner. And so I will have integer values which might be negative. Unsigned, the bits will be treated so that I have unsigned numbers, and so on. I have a special type there, the J type. This ensures that I only have values which fit in both unsigned and signed values, because it reduces the number of methods I have to offer. Then we have a float and decimal. I wasn't interested in floating point and decimal point arithmetic yet, but this will follow soon. The decimal will be oriented at with the new IEEE standard, so you have a decimal format which might be a little bit faster than the big decimal in Java, but this is not sure. But we will see. And then you have the Boolean values, true and false. So as I said, you have special machine words with different width, and you have especially a preferred machine word, which is on a Java virtual machine int, a 32-bit int. You have several properties coming with your machine word. So if, for example, I have a M4, then I have a specific width, a size, and element size. You see the square brackets. This is a unit. So the width is a number and the unit is bit. So I support units. Okay. You see, there are my bytes. They are set arbitrarily, but they are numbered in a specific way. So the least significant bit is always bit 0, and the most significant bit is always bit n minus 1, where n is a power of 2. For example, if we have a tetra, then the width is, of course, 32-bit. The size is 4 byte, the element size is 4 byte, and the alignment is 4. So this means if we want to access a tetra, then we must provide an address which is divisible by 4. Then you have several other possibilities to access a word. And this might be useful. You can always access the high part, the low part. You can access the bytes, the tetras, and so on. So you see, if I have a 32-bit tetra, then you can access the least significant byte, the least significant half. You can, of course, treat it as a signed or unsigned. I'm not sure if this is really needed, because in the embedded area, sometimes it's needed that you need the high byte of the low byte and the low byte of the high byte. That's very complicated. So there's a need for this sometimes, but I'm not sure if it's necessary to have an instruction. The idea is with my instructions is that they will deal with a common case, which leads to a lot of functions. For example, I have, you will see 6 add functions or something, which have different purposes. And if I know the proper purpose, I know how to translate it to for the Java virtual machine or for any other processor. Okay, here's another example. You see there's the high, there's a low. You see which bits are in use. And so I think it's clear. Okay, what kind of intrinsic functions are offered? I have everything which will be needed for bit and Boolean functions. What's interesting is I also offer a not, and the not is not implemented in Java. So if you want to flip all the bits in a word, you need to load -1 and then XOR it with the word you want to flip. So I say there's an instruction, and how it's done, you don't need to cope with it, but there will be a best way to do it on a specific platform. So I know what to do on a Java virtual machine. I have generics. the generics are always in those Oxford brackets, and you see that T is a machine word of a specific size, and if you put in T, you get T out. This is useful, for example, if you have a signed word, then, and if you do something with it, then the signed word will come out, and so on. Okay, then I have functions for the number of leading 0 bits, the number of trailing 0 bits, and so on. And here's important that you know if it's available as a native function. For example, in Java, it doesn't look like that it's native. Because it's, there's an integer, in the integer class there's a function, it's called count bits or number of trailing zeros, and they will be recognized by the virtual machine. So the just-in-time compiler knows that it looks like a static function, but it knows it can translate it to a machine operation. And you don't need to care about this either. So if you use number of 1 bits, then I call the integer bit count function, and this will be, because I know it, will be translated to a machine instruction, which is very fast. If it's not available, you can test this in one of your preconditions, and then you know in a variant that you don't want to use the bit count because it becomes slower. The problem is that we don't know how the virtual machine implementers will do those things, because there is no requirement. If you, for example, take a look at integer bit count, it simply says it counts the number of bits, but it doesn't say if you are building a virtual machine, make sure that this is a machine instruction. And there are, of course, machines where there is no machine instruction for counting bits. Okay. Addition. If you want to add 2 numbers, we can do it. And what is different to Java is, per default, I check if there's an overflow. So if you add 2 signed numbers and the result wouldn't fit into a signed number, then you get an overflow exception. Sometimes I don't want this, so I use add unsigned. The add unsigned and the add function are the same. They have only a different overflow behavior. But the unsigned will never check the overflow, because this is what we are used to. If we deal with unsigned things, then they will wrap around. It's fine. Then to add with larger numbers, a big integer, for example, then we want to add with a carry. So we only have, let's say, 32 bits, but we want to know if we have an addition, if there will be an overflow. This can be checked very simply without an if. So this function offers you the possibility to access the carry bit and to provide a carry bit to have a multi-word addition. Of course, if you edit signed, there's a different overflow behavior, as I said, so we must have an add with carry unsigned add function. And then sometimes you want to add signed and you want to document that this is a signed add, but you know that you won't have an overflow. You simply say add unchecked, and the same with an unsigned value. You want to check if there's an unsigned overflow, then you can do it. So you see, it seems to be very problematic, but it's always the add function, and then you have additional properties what the add will do for you. Okay, same with subtract. Division. Division is a little problem because the division might not work as you expect. Who of you knows that dividing by a power of 2 is the same as shifting? Who of you knows that this is wrong if you have negative numbers? Okay, you see that's a problem because it's non-intuitive, and so we have the possibility to divide in several ways, and these are the 4 most important ways to do it. And you see you can round to minus infinity, or you can round to the nearest, you can round to the to plus infinity, or you can round to 0, which is what the Java function does. So if you have a division in Java, it usually divides by rounding to 0. This leads to sometimes subtle errors shown here. For example, you have those numbers and you have those slots below, and you want to put the numbers in the slots. So let's say we take a look at 2, how we get this in the slot, and every slot can keep 3 numbers. We divide by 3. Okay, 2 divided by 3 is 0. So we put the 2 into the slot 0. Let's do it for 5 again. 5 divided by 3 is 1. It will be rounded as 1 something. It will be rounded towards 0, so it will be 1. Okay, fine. If you do it with the other numbers, they will fit. But if we do it now with -1, we have a problem. By rounding towards 0, what will happen? We want to be it in -1 because we want only 3 elements per bucket. But if we do it in the Java way, we will have an error here because this function is not symmetric. Because -1 divided by 3 is also 0 because it's 1/3. 1/3 rounded to 0 means 0. And so we have in the 0 bucket, we have too many elements. This is wrong. And this leads to errors if you have negative numbers. And I didn't want to do it. So I simply said, okay, I will have the proper function. Another thing is, if you have, for example, 13 elements and you want to put it in boxes with each 4 elements, then you simply call group. And the group gives you the division, but rounds towards plus infinity. So you know that you need 4 boxes. And if you want to know how many elements are missing in the last box, then you use the pet function and it gives you the correct number. So this might be useful. I think it would be more useful in a higher level language, but these operations are offered, and it's a little bit tricky to do it based on the division which is available, but you don't need to care about it. The proper versions are offered. Okay, we have multiplication. It's the same with the add. We have multiplication with carry, which allows us to have a multiplication with several elements. And we have special versions which use shift operators. And if there's a machine instruction available, then we can use the machine instruction. Oh, so we have to hurry up a little bit. We have shift operations. The shift left will overflow. The shift left unsigned will not overflow. This is what we have in Java. We have a lot of other functions which are very, very fine. Okay. Control. We have a Goto. And with the Goto, you give a label. And what might be interesting is you don't need to find proper names. You can simply say Goto1, and the arrow points downwards. You know this one is needed. And if you say Goto1 up, you know it's the one up. This seems to be not a very good idea, but this idea is around since the 50s, and it seems to be a very good idea to have numbers or temporary labels which are only used in a small scope. Please use proper names like loop and init for more interesting things. Then we have jump tables. On the left side, you see that you need a continuous set of numbers. You can, of course, omit some, but if you switch the offset, then you see from 0 it goes to the 0 label. If the value is 1, it goes to the 1 label, and so on. So this is a switch we have, and you can put annotations there to say, please do it this way or that way for the virtual machine. And another thing which is interesting is that you can enhance those mechanisms. Whenever you have a function which gives a number, which you have some elements, you get these elements and you translate them to 0 to n-1, then you can use, of course, the left side, and you can incorporate it very easily, so you don't you can reuse it and you don't need to program it every time. If you have a conditional jump, we write it like this. There's no simple instruction. You simply say if condition, then go to somewhere, and then end if. You cannot put anything else there. This if is specific, and it's only to check the condition, and if the condition holds, you go to the specific place. Everything else is forbidden. everything else is wrong. You have also a conditional assignment. You can put an assignment there if the condition holds. These are the only two possibilities to use an if in this level. These are the predicates you can use on the relations like equal, less, greater than, and so on. There are two exceptions. The use of operators is only allowed in two cases. The one is the Iverson operator, which allows you to have a Boolean expression, a condition, and it gives you the proper bit. So for example, if you want to know if there's an overflow and you have, this is a Boolean condition, do I have an overflow or not? Then you get 0 for false and 1 for true. You see here there's a very efficient way to get the sign. If you, for example, say, give me the value from the positive, if x is positive, then you will have a 0 or 1. And if you subtract from it a 0 or 1, if this is negative, then you have the sign. So this is very interesting and very efficient way, assuming that you have those machine operations. Then we have the target operator, which is a special operator which allows us to get the address of any object we work with. For example, you see there we have in our data segment there's a variable, there's a element x, it's a tetra, and if we say load and we get those the address of x, then we can of course load the proper element. Okay, and now I think we are coming to the interesting part. Sorry that it took so long. We have points and lines. A point has two elements, x and y. A line has 2 points. If we make it in Java, we have to allocate the memory. We have to create a new object, and the object has to be initialized, and so on. Keep in mind that if you have a point, it extends object. So this means that we have additional information, and the additional information might be necessary. For example, if you use hash code and so on. But in our case, it's not interesting now. So a point looks like this, and a line looks like this. If we say in our Java program, give me a line variable, then we have some sort of pointer. And the pointer points to a line if we create one. And then we create points and assign the address, the reference to the line. So this is what a typical object-oriented program will do. How does it look in AL1? We do it in the same way, but we don't call new, we say allocate managed. Because we have also the possibility to allocate memory unmanaged, which might be interesting. So managed code is we don't need to release it, and it can be relocated and so on. This is exactly the same as in Java, and this might be interesting for special cases. Of course, we can also shorten it a little bit if we use the colon arrow notation. And don't forget to initialize your elements. So if you want to initialize your objects, which is necessary in Java, you simply say line.init and give the address of the object to be initialized. Then we have several load functions. We load and store. If we store elements, it will be checked if the value is small enough to be stored in the specific thing. I will skip this. Sorry. And there are special loads for references and pointers. So a managed memory is always a reference. An unmanaged memory can be referred to with a pointer. Okay, and what I want to show you is... Okay. We have 3 ways to allocate memory. Allocate managed. This is what you know from Java, and it will be in the managed memory pool, and you have all the problems you have because it's Java memory and all the advantages. Allocate unmanaged. This gives you a pointer which has to explicitly be released again. So you have an alloc and a free. And this will return a pointer. A pointer is not the same as a reference, of course, because a reference is a number which refers to a place where a pointer is stored, and we cannot access this pointer. This is hidden for us. But this indirection allows the virtual machine to relocate memory, to garbage collect memory, and so on. Okay, if we do it by ourselves, we have all the problems we have with C because we do everything by ourselves. The errors we do, releasing wrong memory, and so on, you can do whatever's wrong. So you must have a good reason to use this feature. And the last thing is we can allocate memory locally. We cannot do this with a virtual machine, but so it will be some sort of managed memory, but you don't see the difference, so it doesn't matter for you. Okay. In AL1, because of the higher levels, you don't say class, you say object, because we describe objects and not classes. If we describe a class, we describe something else. So our object is, I'm sorry, it doesn't seem to be a good idea to change everything. But the problem is that Java is not everything, which means that if you have class, this is the way in C++ and in Java, but there are other languages which use the keyword object. And so I thought it's a better way to describe it because we have also records, and a record is one thing. So the corresponding name for objects is object, not class. Yeah? Oh, okay. So if you translate our Java example, you see we write simply object point, and what happens is that we create a record, and this record extends object maybe, so there are additional informations, and the point name from the object is actually a reference to this created record, just to make sure that they are similar. So if we have a record which will be managed by ourselves, and we have an object which will be managed by a virtual machine, that we have similarities, and we can use it in the same manner. Okay, so let's take a look. We have a line here. We have an array of lines. What will happen? We create a new array in Java, then we create a line, and then we create the points. So this is what we have to do to create a line. And this might look like this. So we have our array with several lines. What we need is a lot of things. And if you sum it up, you have 64n. You need 64 bytes for every entry. And every entry means a line with points. Plus an overhead of 12 bytes. The question now is, can we do it in a little better way? Because if we have to access something here, then we have the problem that we have to first access the line, then we have to access the point, and it would be nice if we can shorten it. We could do it like this. We can embed the points into the lines. So we only need to create one object, but it contains two objects. Each of those objects contains two objects. So let's see. How can we do it? We simply say either record point, so we know that this is something which will be embedded. So our line is something with points, which are records, so it will be embedded automatically. If we don't have access to the object, because point is defined as an object, we simply say embed. And then he knows that he copies the structure and can put the elements into the line. So we get rid of one indirection. Okay, so this is like how it looks before. No, if we embedded the point, but we still have the error problem. And most of the time we deal with a collection or array of lines. So there's a question if we can incorporate the line objects also into the array. And it is possible. Then it will look like this. And it will have many advantages. One advantage is the space. We only need 16n, not 64n anymore. So it will only take a fourth of the space. And let's take a look if we have to access something. If we want to access the y points in each line. So we go and get the first element, then we access the p element, and then from the p element, from the point element, we get the y. If we want to access the next one, we have to get the next line, and then from this line we have to get the correct point, and from this point we have to get the y. If we do it in L1, it looks the same. The only difference is that we have to do everything explicitly, so you say load element reference, so you get the reference of the specific line. Load field reference, then you get the reference of the specific field. And then load field, and then you can load the field y. If you do it again, we have to do everything again. If we can now incorporate this, then we have an advantage. First, it seems that everything is the same. Calculate element address, so it calculates the element address of the specific line. Then we get from the line the specific field address, which is the point. And then from this address, we get the field, the y. Okay, and if we do it again, we have to do it again. Fine. But we know that we can also access these things by pointer. So for example, if you see load field address, and we get now the field address, and now we can do it with load. So the difference is, this is the pointer to the line, and this is the pointer to the point, and this is a pointer to the element. Because this is a pointer, we can misuse it in a proper C way. You see that to access this y and to access this y, we can simply jump our pointer to the next interesting point. So if we know that our delta is 16 because it's 4 tetras, then we can simply say add 16 and then load the element again. So this is an advantage. The first thing is we can compact our elements. They are not distributed in the memory anymore. We can put them in one array sequentially. And if we, for example, loop over those elements, we can use the structure information we have, and we can simply say add 16. And so we can read every point for, let's say, 1 million elements. And sometimes if you have the correct structure, it's more efficient because the things can be prefetched, so you have no caching problems, and so on. But you have to be very careful because the virtual machine is very clever, and most of the time those indirectional structures can be handled very efficient, and you must be sure to use this way, and you have to test if you have the results you expect. Okay. This was a lot of stuff. We have 2 minutes for questions. Yes?
Do you type all that Unicode?
How I type all that Unicode? I have... Just a second. I don't know where my window went. Okay. You know this from Word. If you type, for example, minus and then greater, it shouldn't be a problem. I don't have the time to write an Eclipse plugin or something, but it's no problem. On the Mac, you can use, for example, those tables, and you get used to it. So if you need anything within a short time, and I expect that there will be something in the editor where you can use the mouse, or you can type the things, you can type tech names or whatever, and whatever. Other questions? This is interesting. Most of the time the people ask me, is your keyboard big enough, and so on. So the only problem the people seem to have is, how can I enter the information? What I want to do is I want to offer a possibility to read the things properly. For example, if you use a mathematical-like notation, the chances are very high that somebody understands something which says, if blah, 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 then, and then you make an assignment with an arrow. You, of course, can learn everything. And you, of course, can learn everything. And if you have learned everything, everything's fine. So it seems time's up. Thank you for your patience, and have a nice day.